I mentioned multiple times that rates of sedimentation may not be constant. Now is a great time then to investigate what happens when you change rate of sedimentation. So let's look at a few examples on a 2D diagram first, and then as usual we'll do some modeling to convince ourselves that this process indeed plays a major role. So here's an example of a shoreline where we have a relative rate of sea level rise. So you can see we have a relative rise in sea level or base level from initial to final. And at first we have very low terrigenous influx. So we don't completely feel this accommodation that we create. And the net impact of this is because we don't feel accommodation, we have a transgression. But what happens on the same shoreline if we change the rate of sedimentation? So here we have a situation where we have a shoreline with a relative rise in base level from an initial value, that's the dashed line, to a final base level position. Now that relative rise is unfilled by sediments because we have low terrigenous influx. So when that is the case, because we do not feel accommodation, we have a transgression and the beach facies migrates towards the continent as we have seen. But what would happen to the same shoreline if you change the flux of sediments? If you have a high terrigenous influx, then you completely fill that accommodation. Notice that the relative rise in the creation of accommodation is the same as in the previous example. But because this accommodation is filled, we have a normal regression. And of course, that means that the shoreline is migrating towards the center of the basin. And then finally, if you have a balanced terrigenous influx, so as much sediment is inputted as you create accommodation, then what you expect is an aggradation. So in other words, the shoreline is neither moving towards the continent nor towards the basin. You're just filling the accommodation that you are creating. So again, that drives home the point that the sedimentation rates play a major role in controlling the sequence stratigraphic architecture of a given basin or a given margin. It's not just base level rise, base level fall, it's base level rise, base level fall, and sedimentation rate. And here you have all three cases together, and it's really important to notice that this relative rise in base level is the same, but the architecture of the sediment is completely different. So always keep that in mind. Now we can actually look at some modeling examples. And also I want to show you an example where essentially we create accommodation in the basin in unequal proportion. Because so far we've only talked about subsidence of a whole margin. But what happens if you have faulting, if you have some type of block faulting happening, if you have one area where you create a lot of accommodation, whereas the rest of the margin you don't create as much accommodation. So let's look at some modeling examples to understand what happens there. So at first I'll show you the model that I've created. It's a cross-section of the model. Again, it's a simple ramp, but I won't put any sediment in, so we'll just look at the response of basement. So here we have a situation where the ramp has an internal area where you have more subsidence. So we're creating a mini basin within the ramp, and that's called differential subsidence, where the subsidence is not equal. Again, you could imagine that in this area here, you might be fault bounded and you're looking at a pull apart basin or maybe tilted margin. It doesn't really matter. The point is, this is typically what you would expect if you had tectonic. Now notice that sea level is constant. I'm not changing base level here. The subsidence in the graben is about 20 meters. The subsidence on the ramp is 0 meters. So there is no regional subsidence, there is no base level change. And in this first example, the sediment supply is 0 cubic meter per million year. So now let's look if we change those sediment supply, what happens. So that's the same example, except that this time I have 12 cubic meter of sediment coming per million year. And notice that in this case, the sedimentation rate and the accommodation creation in that basin is pretty well balanced. And what happens then is that we have aggradation of the sediment in the basin, and the sediments are fully trapped in this mini basin. They do not prograde over the ramp because we create enough accommodation in this basin to trap sediments. So that's perhaps the first lesson here about these differential subsidence model, is that when you look at a real example of a margin, especially a tectonically active margin, it's more complicated because sediment flux can be captured by area of high subsidence. You can create mini basin catchment of sediments. So now let's look at a case where the sediment supply is higher than 12 cubic meter per million year. In this case, I'll take 60 cubic meter per million year. The ramp is the same. Just notice that I've changed the geometry because I've changed the vertical exaggeration just to show those sediments nicely. And it's very clear. You can see a clear evidence here of progradation. I put so much sediment in the system that my beach sand is prograding, and I've completely filled now the mini basin. And in fact, so much so that now I'm filling accommodation on the ramp, and I have a huge pile of continental deposits in the back here. So again, the key is that sediment supply is really important for the sequence stratigraphic response of a particular system.